Muy buenas tardes, bienvenido a nuestro séptimo webinario Alhsud 2023, ¿verdad? En esta oportunidad titulado Sobre el correcto uso de modelos hidrogeológicos en la toma, ¿verdad?, de decisiones, o modelos hidrogeológicos o hidrológicos, como quieran denominarlos. Hoy en día los resultados de los modelos hidrológicos se utilizan a menudo como evidencia para guiar decisiones que abarcan desde la evaluación de recursos hídricos hasta la evaluación ambiental de nuevos proyectos económicos en sectores como la minería, la energía y la agricultura. El uso de los modelos para estas aplicaciones se preocupa principalmente por predecir el valor futuro de una o unas pocas variables de interés, lo que a veces se confunde con el esfuerzo por modelar de cerca la dinámica de los sistemas naturales complejos a gran escala como la hidrosfera o los acuíferos. Esto a menudo resulta en una aplicación incorrecta de modelos para respaldar decisiones. En esta presentación discutiremos por qué. Básicamente desde dos ópticas. No podemos tomar los resultados de los modelos o del modelo demasiado literalmente, ya que son malos simuladores del comportamiento ambiental. Y por otro lado, simular el comportamiento ambiental no es el punto. La cuestión es reducir y cuantificar la incertidumbre en las predicciones de interés, que son dos cosas distintas. En esta oportunidad expone John Doherty, geofísico de exploraciones y modelador de aguas subterráneas. Es autor de PEST, el paquete de software más utilizado para la calibración autónoma de modelos hidrológicos. Actualmente trabaja a través de su propia empresa, en consultoría, investigación y educación sobre temas relacionados con el despliegue de modelos en apoyo de la gestión ambiental y la evaluación de impacto. Es autor de más de 30 artículos técnicos sobre estimación de parámetros y análisis de incertidumbre aplicados a modelos de aguas subterráneas. La Asociación Nacional de Aguas Subterráneas de Estados Unidos le otorgó la conferencia de Doherty en 2019 por su destacada contribución a la hidrología de las aguas subterráneas. Lo acompaña en esta oportunidad, ¿verdad?, que también realizará una ponencia, Paulo Herrera, PhD, ingeniero civil, ¿verdad?, y PhD en ingeniería geológica. Ha sido consultor en Chile y Canadá e investigador en Noruega y Austria. También ha dictado cursos a nivel de pre y posgrado en la Universidad de Chile, Técnica Federico Santa María, Adolfo Ibáñez, British Columbia y Viena, en temas relacionados a recursos hídricos. Ha sido coautor de más de 20 artículos técnicos publicados en revistas especializadas y conferencias internacionales y nacionales. Como es habitual, realizaremos las ponencias en primer lugar y luego daremos un espacio para consultas. Les recuerdo que los webinarios del Alhsud son grabados y quedan después disponibles para todo público en la página web. En esta oportunidad, como tendremos un seminario híbrido donde Paulo hablará español y John en inglés, ¿verdad?, tendremos un apoyo para las consultas y Carlos Chapa también me apoyará con hacer una presentación en inglés del inicio del seminario. Así que, Carlos, y después tú das la partida nomás para que partirá, entiendo, Paulo, que partes tú y después viene John.
Perfecto, Pablo, muchas gracias. Well, good afternoon. Welcome, everyone. As Paulo said, we are happy to present today two prestigious professionals in our 7th webinar talking about the correct use of hydrological models in decision making. Nowadays, the results of hydrological models are often used as evidence to guide decisions that span from water resources evaluation to environmental assessment of new economic projects in sectors like mining, energy, and agriculture. The use of the models for those applications is mainly concerned about predicting the future value of one or a few variables of interest, which sometimes is confused with the efforts to closely model the dynamics of large-scale complex natural systems, such as the hydrosphere or regional aquifers. This often results in a wrong application of models to support decisions. In this presentation, we will discuss why. First, we cannot take models' outputs too literally, as they are poor simulators of environmental behavior. And secondly, simulating environmental behavior is not quite the point. The point is to reduce and quantify the uncertainties of predictions of interest, These are two different things. The exhibitors presenting today are John Doherty, PhD. He is an exploration geophysicist and groundwater modeler. He is the author of PEST, the most widely used software package for automatic calibration of hydrological models. Currently, he owns a consultancy company named Watermark Numerical Computing, focused on research and education for the deployment of models supporting environmental management and impact assessment. He is the author of more than 30 technical articles on parameter estimation and uncertainty analysis applied to groundwater models. And in 2019, the US National Groundwater Association awarded him with the Darcy Conference for his outstanding contribution to groundwater hydrology. On the other hand, we have Paulo Herrera, also PhD. Paulo is a civil engineer and a doctor of geological engineering. He has been a consultant in Chile and Canada and a researcher in Norway and Austria. He is an undergraduate and postgraduate professor at the University of Chile. He has been an undergraduate and postgraduate professor at the University of Chile, Universidad Técnico Federico Santa María, Universidad Adolfo Ibáñez, University of British Columbia, and in Vienna, on topics related to water resources. He has co-authored more than 20 technical articles published in specialized journals and in international and national conferences. As Paulo said, firstly, we will have the presentations, and afterwards, you are all invited to do your questions or consultations, and we will be supporting with the translation of those for John or Paulo. So, say no more. Paulo, you have the floor, and thank you for being with us tonight.
Muchas gracias, Carlos y Pablo, por la introducción. Voy a compartir mi pantalla acá. Y me gustaría chequear primero si están viendo la presentación.
Se ve, pero
Sí,
se ve
perfecto. Ahí quedamos.
Ahí estamos. Entonces, me gustaría partir por agradecer primero a los participantes. Veo que en este momento hay 55 personas conectadas. Entiendo que hay personas de fuera de Chile también, de Perú, vi ahí en el chat que hay algunas personas, así que muchas gracias por su interés. Espero que el seminario les resulte interesante. Quería agradecer también a los organizadores, al Alhsud, a Pablo y Carlos por su ayuda para organizar este seminario, y muy especialmente a John Doherty por su disposición, digamos, a conectarse a esta hora de la mañana desde Australia. Son las 7 de la mañana ya. Así que el objetivo de esta presentación es hacer una introducción a la presentación de John. Y bueno, Pablo y Carlos han hecho una introducción a John. No voy a repetir toda su biografía, digamos, pero comentarles que conocí a John hace varios años ya en un curso que él dictó acá en Santiago, y después nos hemos encontrado por distintas razones en distintos lugares y en distintas instancias. John es una persona muy conocida en este tema en particular, la estimación de parámetros para modelos hidrogeológicos y el análisis de incertidumbre, que es un tema que es un poco más técnico y que por lo menos en Chile tiene menos desarrollo que la estimación de parámetros. John ha sido, digamos, a seminarios en distintos lugares. Esto lo tomé de su página, de la página de su compañía. Entiendo que la próxima semana está en Suiza dictando un curso, y a principios del próximo año va a estar en Estados Unidos, o va a participar en un curso en Estados Unidos dictando otro curso. Y entonces mi presentación tiene como objetivo, yo llevo pocos años en comparación a John estudiando este tema. Partí, de hecho, estudiando un libro que él publicó, digamos, que él escribió y publicó, que lo recomiendo para las personas que estén interesadas, tengan mucho o poco de experiencia en este tema. Encuentro un libro bastante interesante, bastante completo, y por lo tanto pensé que debía o sería bueno hacer esta presentación para introducir un poco el tema desde la perspectiva de una persona que no tiene tantos conocimientos como los que tiene John, y también porque quería poner el contexto nacional de Chile en la aplicación de este tema. Entonces, el título de este seminario es Models for Decision Support, modelos para la toma de decisiones, y quería partir por explicar un poco a qué nos referimos con eso. Voy a partir con un ejemplo que es bien típico en el norte de Chile, un ejemplo de un salar, que es lo que se muestra acá en la foto, en el del cual se quiere extraer agua. Y entonces tenemos un pozo que está a cierta distancia de las márgenes del salar, donde se producen afloramientos de agua y se crean ecosistemas en lugares donde en general hay muy poca agua y por lo tanto estos ecosistemas son bastante importantes. Y entonces muchas veces uno se encuentra con proyectos en que lo que se quiere responder es una pregunta tan básica como ¿cuál sería el descenso si yo bombeo agua, extraigo agua? ¿Cuál sería el descenso que se va a producir en la margen del salar? Porque eso puede tener un potencial impacto ambiental. Y eso lo puse acá abajo, puse referencia a un proyecto cualquiera, digamos, porque hay varios estudios de impacto ambiental que en Chile están publicados, se pueden consultar, que tratan estos temas, tienen distintos enfoques de modelación. El objetivo mío no es discutir un proyecto en particular, sino dar una visión general de esto. Entonces, este es un tema que se está haciendo en la práctica. Ahora, lo que ocurre en muchos casos es que dependiendo de la pregunta que nos dé el modelo, el proyecto que se quiera realizar puede hacerse factible o el proyecto no puede hacerse, es rechazado. Y entonces, si queremos saber cuál es el descenso en la margen del salar, una respuesta bien habitual es decir, vamos a construir un modelo para evaluar eso. Y eso es a lo que nos referimos en el uso de modelo para la toma de decisiones. Dependiendo del resultado del modelo, tal vez nosotros decidimos hacer el proyecto o decidimos no hacer el proyecto, o la agencia que está a cargo de dar los permisos va a decidir otorgar el permiso, o va a decidir no otorgar el permiso, o va a pedir algún trabajo adicional. Ahora, en Chile este tema se ve a menudo. Estos son párrafos que tomé de documentos oficiales que están en la web de presentaciones que se han hecho ante el Servicio de Evaluación Ambiental. Entiendo, borré todo lo que me pareció que era específico en cierto proyecto, porque lo que quería hacer hincapié acá es que en el caso de los salares hay una norma que se ha aplicado que dice que si el descenso es mayor a 25 centímetros, entonces podría existir un cierto desmedro al medio ambiente, a los ecosistemas, y por lo tanto puede ser un problema. Ahora, en general eso se aplica a observaciones, digamos, se instalan piezómetros y se observa, se pueden monitorar los descensos, pero antes de que se ejecute el proyecto y no existen esos piezómetros, se utilizan modelos, y el último párrafo es lo que está acá, yo no sé si ustedes ven mi cursor, eh, para, eh, para evaluar antes de ejecutar el proyecto cuál sería el potencial impacto de extraer, por ejemplo, una cierta cantidad de agua. Entonces ahí es un ejemplo claro de que en la práctica se están evaluando proyectos que pueden involucrar inversiones bien grandes, que pueden dar también, por ende, trabajo a muchas personas, eh, en base a los resultados de un modelo numérico como en los que nosotros trabajamos habitualmente. Ahora, ¿qué es lo que entendemos por modelo? Ahora quería entrar a la otra parte del título, y para eso voy a ocupar un ejemplo que es muy simple. Está bien explicado en un artículo que acaba de aparecer en la revista Groundwater, y el ejemplo está basado en el caso hipotético de un acuífero que está entre dos ríos que tienen distintos niveles piezométricos conocidos, H1, H2, y para efecto de simplificarlo aún más, hacerlo más sintético, asumimos que solo hay la posibilidad de tener dos valores de conductividad hidráulica, dos tipos de roca, de material, de tal forma que podemos caracterizar el sistema por un valor de K1 y K2, y que a lo largo de este acuífero existe una recarga, y esa recarga vamos a asumir, para hacerlo más simple todavía que la realidad, que es una recarga uniforme y que de alguna manera podemos evaluar, digamos. Pero en principio este modelo, entonces, este problema tiene tres parámetros que son importantes, son los dos valores de conductividad hidráulica y el valor de la recarga. Ahora, si queremos desarrollar un modelo matemático de este problema, una opción es hacer un modelo en base física, y en el caso de la hidrogeología, el agua subterránea La primera ecuación con la que uno parte es la ecuación de García, una ecuación eminentemente empírica que fue desarrollada en base a los resultados de experimentos, ¿no es cierto?, hace aproximadamente 150 años. Después aplicamos un concepto muy útil en ingeniería hidráulica y en hidrología, que es el balance de masa. Decimos que lo que entra menos lo que sale tiene que ser igual a la variación de almacenamiento en el sistema. Si el sistema asumimos que no tiene variaciones temporales, entonces la variación de almacenamiento es cero. Y con eso, sustituyendo los flujos dentro de esta ecuación de balance de masa, vamos a llegar a una ecuación diferencial parcial, que es la que está presentada acá arriba. Básicamente uno llega a esta ecuación diferencial parcial, que es muy simple para este problema. Y para este problema podemos encontrar una solución analítica, y una solución analítica que tiene esta forma. Dice que el nivel piezométrico o el nivel freático a lo largo de ese acuífero está dado por esta ecuación que está acá, donde esta X, que debía haber mostrado la figura, es la distancia desde el borde izquierdo. Estos parámetros A, B y C dependen de los parámetros del problema de K1, de K2 y de la recarga, además de la variable independiente, en este caso que es X. Como asumimos que este es un problema de que es de régimen estacionario, no existe la variable tiempo, pero eventualmente acá podría también aparecer en verde, digamos, como variable independiente del tiempo. Ahora, si queremos evaluar cuál es el nivel de agua a lo largo, el nivel freático a lo largo de ese acuífero, ¿no es cierto? Vamos a construir un modelo, y acá simplemente el modelo le designé con una letra M, porque hasta ahora no hemos dicho qué tipo de modelo va a ser. Este puede ser nuestro modelo. Simplemente tomamos la raíz cuadrada de esta expresión y obtenemos este modelo que está acá. Y podemos evaluar y obtener, para distintos valores de los parámetros, podemos obtener distintas superficies del nivel freático. Ahora, lo importante acá que quiero concentrarnos ahora son en estos tres valores acá que vamos a llamar los parámetros del modelo. Son valores que a priori no conocemos y que tenemos que estimar de alguna forma, ¿no es cierto? Ahora, tenemos otro tipo de solución si no queremos entrar en matemática, digamos, que no es muy difícil, pero si lo queremos hacer de otra forma, existe la posibilidad de resolver esa ecuación diferencial de forma numérica, que es lo que hacemos, por ejemplo, con un simulador tipo modelos o con FIFLOW. Y ahí tenemos otro tipo de problema, porque vamos a dividir el dominio ahora en celdas de distinto tamaño, ¿no es cierto? Y entonces sabemos que si las celdas son muy grandes, vamos a introducir un error matemático, puramente matemático, pero también sabemos que si las celdas son muy grandes, vamos a introducir problemas al asignar parámetros, porque, por ejemplo, podemos tener un acuífero que tenga mucha heterogeneidad, digamos, distintos tipos de material geológico con distintos valores de K. Si tomamos una celda, como lo hacemos a veces en los modelos ModFlow, de 200 por 200 metros por 50 metros de alto, qué valor de K representa el que estamos poniendo en el modelo, digamos, representa el que estamos midiendo en una prueba de bombeo, el que estamos midiendo en un slack test, el que medimos en un ensayo de laboratorio. Podemos calcular ese parámetro. Muchas veces sabemos que no lo podemos calcular porque el tamaño de la celda es muy grande, no corresponde al tamaño en el cual estamos observando. Ahora podemos tener otro tipo de problemas también, y es que como en el modelo numérico podemos tener tantas celdas como queramos, eh, nosotros podemos tener infinitos valores de conductividad hidráulica, por ejemplo, y tener infinitos parámetros en el modelo simplemente por ocupar muchas celdas. Si asignamos un valor de cada celda, entonces llegamos a tener casi infinitos parámetros, que son difíciles de estimar, y entonces el problema, en vez de estimar 2 parámetros, podemos estar estimando 100 parámetros, 200 parámetros, 500 parámetros del problema. Y eso en sí es un problema. Ahora, desde un punto de vista puramente numérico, como dije, podemos tener diferencias, y eso es lo que muestra este gráfico de la derecha acá. Esto muestra simulaciones de este problema con ModFlow ocupando dos solvers numéricos. Para las personas que ocupan ModFlow, probablemente esto les va a resultar bien familiar. El solver Newton, que es el nuevo, el que se recomienda, y el no Newton, que es el solver más antiguo, que está en versiones anteriores a ModFlow NWT. Y si uno compara las dos soluciones para la misma grilla, con las mismas condiciones, exactamente el mismo, se da cuenta que hay una diferencia en las soluciones simplemente por un efecto numérico. Esa diferencia en algunos casos puede ser significativa, en otros casos puede ser no tan significativa, pero está ahí y algo con el cual tenemos que tener en mente cuando comparamos resultados de este tipo de modelos. Ahora, si no queremos o no sabemos nada de los principios físicos con los cuales se mueve el agua subterránea, podemos también intentar ocupar un modelo tipo black box, o si quieren de machine learning, que es un nuevo término, en el cual es un modelo puramente matemático. Sabemos que tenemos tres parámetros, tratamos de ocupar esos tres parámetros con alguna expresión, por ejemplo, un polinomio, para poder estimar el valor de h. Ahora, en este caso acá, simplemente ocupé una combinación lineal de los parámetros del problema, y entonces nos aparecen estos parámetros que designé como alfa, alfa 1, alfa 2, alfa 3 y alfa 4, que son parámetros puramente matemáticos, no tienen un significado físico, no están necesariamente asociados a ninguna cosa, y nosotros los podríamos estar estimando. Podemos también tener un modelo en base a redes neuronales, que es un modelo matemático más sofisticado, ¿no es cierto?, donde podemos tener como entrada los dos valores de permeabilidad, tal vez la recarga, y podemos tener conexiones que vamos a designar como parámetro alfa también, que nos van a dar finalmente, esa es la combinación de los parámetros de entrada ponderados por estos factores que tenemos acá, nos van a dar el nivel piezométrico. Lo importante y lo que quiero decir acá es que en cualquier caso nos van a aparecer ciertos valores, ciertos parámetros que no tienen un significado físico y que por lo tanto algunas veces uno lo ve referidos como pseudoparámetros, superparámetros en el lenguaje que John va a ocupar en la presentación de después, o yo le llamo acá future parameters, que son básicamente parámetros que no tienen un significado físico definido. Acá tomé la definición del diccionario en inglés, que dice que es un término matemático arbitrario que se incluye en un cálculo para llegar a una solución esperada o permitir errores que son especialmente difíciles de no incluir. Y la otra que encontré más sucinta y tal vez más clara es que dice que cualquier factor arbitrario que no está especificado. Eso quiere decir que tanto estos parámetros, todos estos parámetros alfa en el fondo representan cosas que no conocemos, que simplemente se usan ahí para ajustar. Dado que tenemos ciertos parámetros, queremos tener un resultado, lo ocupamos para eso. Ahora, anteriormente les mostré los parámetros A, B y C en la ecuación que derivamos a partir de la ley de Darcy. En muchos casos esos parámetros también, aunque uno trata de asociarlos a parámetros físicos como la conductividad hidráulica, la recarga, también corresponden a parámetros que son puramente matemáticos en varios modelos numéricos, y eso también es algo que hay que tener en consideración. Típico ejemplo en Modflow es el valor de la conductancia de un dren, digamos, que a pesar que se le ha tratado de dar una representación física, es bien difícil muchas veces de ajustar en base a valores físicos. Ahora, cuando tenemos un modelo que depende de estos parámetros, y acá tengo que hacer una mención, digamos, cuando uno tiene este problema, es fácil de mostrar mediante la solución analítica y está hecho en ese artículo que les comenté. Los parámetros de conductividad hidráulica y recarga están correlacionados, por lo tanto, la recarga nunca es bueno incluirla dentro del modelo como un parámetro a calibrar, sino que tiene que ser como un parámetro externo que calculamos de otra forma. Entonces, digamos que nos quedamos con estos dos parámetros, los dos valores de conductividad hidráulica. A priori no lo sabemos, entonces, ¿qué podemos hacer? Bueno, hacemos calibración o lo que se llama resolver el problema inverso o de estimación de parámetros. Y eso quiere decir, digamos que tenemos un par de puntos donde conocemos el valor de H del nivel piezométrico o del nivel freático. Y entonces ahora podemos comparar nuestras soluciones del modelo para distintos valores de parámetros y vamos a tener algunos que nos van a ajustar bien los valores observados y entonces decimos, esos son los valores de parámetros que corresponden a nuestro problema. Como ustedes ven acá, tengo dos tipos de soluciones, una solución en que tengo los dos valores de conductividad hidráulica que son iguales, que este que está acá a la izquierda, y otro en que los valores de conductividad hidráulica son distintos, el K1 es distinto al K2, y vemos que los datos que tenemos en este caso, que corresponden a estas cruces, ajustan mejor el modelo aunque los dos valores de K son distintos. Por lo tanto, acá podemos hacer una discriminación también, decir, un modelo tan simple con un solo valor de K no va a funcionar, tenemos que ocupar dos valores de K. Entonces, más formalmente o más matemáticamente, lo que se hace es, tenemos estas observaciones y comparamos esas observaciones con los valores del modelo dados ciertos parámetros, calculamos la diferencia y después tenemos dos posibilidades. Calculamos cuáles son el conjunto de parámetros que nos da un valor mínimo a esa diferencia, lo cual es bastante costoso en términos computacionales y bastante difícil cuando uno tiene varios parámetros. O ocupamos otro criterio en que decimos cualquier combinación de parámetros tal que la diferencia sea inferior a cierto valor que vamos a asignar como una tolerancia, es un buen parámetro, es un buen set de parámetros calibrados. Y por supuesto también podemos imponer otras condiciones como que los valores calibrados de la conductividad hidráulica tienen que estar en un cierto rango de valores, ¿ok? Que viene más bien de la descripción conceptual del problema. Ahora aquí hay un tema práctico, digamos, y es decir, ¿cuál es ese valor de la tolerancia que vamos a dar, que vamos a aceptar que un modelo esté calibrado? Entonces, acá está el típico gráfico de calibración, que las personas que han trabajado con modelos, yo creo que los deben haber visto, en que tenemos valores observados, valores simulados. Se supone que un modelo bien calibrado, todos los puntos debieran caer sobre esta línea de 45 grados. Eh, y podemos calcular la diferencia, digamos, y podemos calcular la diferencia normalizada, que se llama, que es básicamente la diferencia al cuadrado, la suma de la diferencia al cuadrado dividido por el rango de valores que tenemos a calibrar, ¿ok? Y eso en el caso de Chile está especificado en una guía que existe para la elaboración de modelos para evaluación ambiental, modelos de agua subterránea para evaluación ambiental. Y acá remarqué una oración, un párrafo que tiene esa guía, en que dice, y acá se dice a modo referencial como una sugerencia, un valor de esa diferencia normalizada inferior, igual o inferior a 5% de los niveles piezométricos puede ser considerada como un error aceptable, que dice como una cota máxima de error aceptable. Entonces, ¿qué es lo que ocurre en la práctica? Muchos modeladores nos hemos encontrado que aunque en algunos modelos que son relativamente complejos, es difícil cumplir con este valor. Las calibraciones dan errores que son más altos, errores más, y entonces nos vemos obligados básicamente a ajustar muchos parámetros para poder cumplir con esta tolerancia que en algunos casos puede ser bastante acotada. Ahora acá hay un tema, y eso creo que es importante el seminario de John. Hay dos temas implícitos. El primero es que un modelo que tenga una diferencia muy pequeña es un buen modelo, y por eso se dice acá como una cota máxima. Y John va a conversar, va a explicar mejor que yo, digamos, que tal vez eso no es tan correcto o no es tan directo, digamos. Y lo segundo es que esto que está como una sugerencia, en la práctica muchas veces se ha adoptado casi como una norma o una ley inamovible, digamos, en que si el valor es superior al 5%, entonces el modelo no es admisible o está mal calibrado. Y no es el espíritu, si uno lo lee acá, no es el espíritu con el que está escrito esto. Entonces, ¿cuál podría ser un buen valor? Es una cosa que es un poco más compleja de definir y un poco más subjetiva. Yo creo que la charla de John va a dar algunos elementos de juicio para poder obtener un valor que sea, o por lo menos definir algún criterio que nos permita discernir si un modelo es razonablemente bien calibrado o no es razonablemente bien calibrado. Ahora y aquí ustedes se van a dar cuenta por qué escogí este problema con solo dos parámetros, porque me permite hacer este gráfico que es bastante didáctico, y este gráfico lo tomé, está en el libro de John Doherty, la primera vez que lo vi y lo encontré muy bueno. Es básicamente para este problema que tiene dos parámetros, la conductividad hidráulica K1 y K2, para la cual definimos ciertos rangos de valores mínimos y máximos. Entonces nosotros corrimos el modelo y calculamos las diferencias entre valores observados y simulados. Obtuvimos estos deltas y uno lo puede graficar en este plano, con este espacio de parámetros, que en 2 dimensiones posible, cuando tenemos 3, 4, 5 parámetros, ya comienza a ser muy difícil visualizar estas cosas, pero uno puede hacer lo mismo, digamos, con superficies, volúmenes, etc. Uno se va a encontrar con que si definimos una cierta tolerancia, digamos, todas las combinaciones de parámetros, tal que la diferencia entre valores observados y simulados sea inferior a esa tolerancia, entonces definen una región en este espacio que es una región donde tenemos una buena calibración. Ahora ustedes ven acá, no puse valores exactos, pero uno se da cuenta que hay varias combinaciones de K1 y K2 que satisfacen esta condición, por lo tanto son soluciones aceptables para un modelo calibrado. Por lo tanto existe no una, sino que más de una solución que sea aceptable para este problema, y ese es un tema que es bien conocido en el problema de estimación de parámetros o resolver el problema inverso. Hay otras razones también, pero esta es una. Finalmente, ¿para qué queremos un modelo matemático? Es para tomar decisiones, y eso quiere decir muchas veces simular el futuro, simular condiciones que no son las actuales o las cuales no conocemos. Y entonces nosotros podemos tomar nuestro modelo con los valores de K calibrados para un cierto valor de recarga y decir qué pasa si nosotros cambiamos la recarga. Y podemos tener una serie de recargas. En el caso de Chile, en algunos casos se pide evaluar los próximos 100 años e incluir el cambio climático. Y entonces podemos generar una serie de recargas para los próximos 100 años con el efecto del cambio climático, lo cual puede ser complejo, pero digamos que podemos hacerlo. Dado que tenemos nuestro modelo calibrado, nosotros ahora podemos ocupar el modelo para evaluar esos escenarios y hacer un análisis probabilístico, en el sentido que podemos tener un rango de soluciones, son todas estas líneas grises de acá, y una solución que es la más probable, que en este caso la tracé simplemente como la línea que pasa por el medio de esta otra gama de soluciones. Y eso es lo que se conoce como el problema de pronóstico, y muchos de los modelos que ocupamos para la toma de decisiones se desarrollan para hacer pronósticos, no para evaluar lo que ocurre ahora, sino que para evaluar situaciones hipotéticas, qué ocurriría con el proyecto, qué ocurriría si se reduce la recarga, qué ocurriría si aumentamos el bombeo, etcétera, etcétera. Ahora, existe otra forma de abordar este problema, y es una forma que John va a comentar y pensé que era bueno introducirla, que tiene un enfoque estadístico. Y es, para los que son geólogos, son hidrogeólogos o han trabajado en este tipo de problemas, saben que la forma que uno tiene muchas veces de comenzar a definir valores para estas propiedades, por ejemplo, la permeabilidad, uno va, ve si es que hay recuperación de testigos en sondajes que se pueden haber hecho, hay descripciones del tipo de roca, y después va a una tabla como esta, que la tomé del libro Groundwater de Fries and Cherry, que tiene, ¿no es cierto?, los valores de conductividad hidráulica para distintos tipos de roca. Entonces, digamos que en este sondaje en particular se describió una roca fracturada metamórfica, y entonces vamos a esta tabla y sabemos que los valores de conductividad hidráulica pueden variar para ese tipo de roca en 4 órdenes de magnitud. Y yo siempre hago hincapié en esto, que son órdenes de magnitud, no son simplemente, no es un factor 4, sino que son un factor 10.000 en este caso, para un mismo tipo de roca, que es la información que nosotros en general vamos a obtener de un sondaje. Entonces podríamos decir el camino es 10 elevado a menos 2, el K máximo, o el camino, perdón, es 10 elevado a menos 6, el camino es 10 elevado a menos 2, y quedarnos con eso. O podemos decir, dado que tenemos ese tipo de roca, en realidad vamos a tener una distribución de probabilidades para asignar el valor de ese K, donde el valor promedio probablemente va a ser el valor que tenga la máxima probabilidad. En este caso simplemente asumir una distribución gaussiana. Y los valores más extremos van a ser valores con menor probabilidad. Cuando hacemos eso, construimos una curva de probabilidad, que es lo que se llama una distribución de probabilidad a priori, y que está basada en lo que se llama conocimiento poco sólido, porque está basada simplemente en la descripción de la roca. Ahora, cuando a eso agregamos la calibración, eso quiere decir comparar resultados del modelo con observaciones de niveles, no tan solo con el tipo de roca que tenemos ahí, sino que dónde está la posición del nivel freático en la realidad. Vamos y medimos la posición del nivel freático y lo comparamos con nuestro modelo, entonces podemos ajustar esa distribución de probabilidades porque van a haber muchos casos, los casos extremos, por ejemplo, en este caso, que tal vez van a fallar, no van a estar en el rango de calibración. Y por lo tanto, la probabilidad de que ellos sean parámetros aceptables para el modelo es casi nula o muy baja. Y por eso que la curva de la distribución de probabilidad se ajusta acá. Y entonces estamos corrigiendo esa distribución inicial, la estamos corrigiendo ocupando información que tenemos. Finalmente, como ahora tenemos una distribución de K, no conocemos a ciencia cierta cuál es el valor de este K1, sino que tenemos un rango posible con una cierta distribución de probabilidades. Cuando hacemos pronóstico, por ejemplo, queremos simular el nivel piezométrico en un punto en particular para distintos valores de recarga, el valor de K puede variar, por lo tanto no podemos entregar simplemente una curva, sino que tenemos que entregar una curva que sea la más probable con un rango potencial de variaciones. Y eso es lo que se conoce la distancia entre estas dos curvas rojas, que serían los rangos posibles que podemos tener, lo que se conoce como incerteza o incertidumbre paramétrica, debido al valor, en este caso, del parámetro K1. Puedo tener también para este problema incertidumbre paramétrica debido al valor del parámetro K2. Y ustedes se imaginan que cuando hay modelos que tienen 50 parámetros, podemos tener incertidumbre respecto a cada uno de esos parámetros, por lo tanto la incertidumbre global del modelo puede ser más alta que por un modelo que tiene menos parámetros, por lo menos en esta incertidumbre paramétrica. Y finalmente tenemos otro tipo de problema, que es lo que se conoce como errores estructurales del modelo o incerteza estructural, y que para este problema específico, este problema sintético, se traduce en decir, ¿cómo sabemos que tenemos solo 2 valores de K? Podríamos tener 10 valores de K. A lo mejor el acuífero es mucho más complejo desde el punto de vista geológico. John va a mostrar un ejemplo en que él dice hay una falla, y esa falla entonces, ¿cómo la simulo? ¿Qué es lo que significa? Y hay otros problemas incluso que parecen más simples, es decir, cómo sé el largo de esta zona, incluso si sé que solo hay 2 valores, que fuera un sistema tan simple, ¿cómo es el largo de esto? Entonces uno puede empezar a cuestionarse y decir, bueno, hagamos un modelo que tiene 10 valores de K, que tiene 50 valores de K, pero eso significa hacer muchos modelos, tantos modelos como el número de parámetros que queremos evaluar en este caso, lo cual puede ser bastante costoso y requiere mucho esfuerzo adicional, tanto desde el punto de vista computacional como de análisis, de pensar el problema, pero esa es la forma más común y simple y más robusta de abordarlo, es crear varios modelos que pensamos que son posibles, plausibles, y evaluar la incertidumbre en base a todos esos modelos. Acá puse un par de referencias, son artículos que he escrito con colegas coautores de la Universidad de Viena, que son relativamente recientes. Hay un artículo que es un artículo review de este tema que creo que le puede interesar a varias personas que quieran tener una introducción relativamente simple al problema. Y está este otro artículo que es más un tutorial de cómo aplicar estos conceptos a este problema en particular. Así que con eso ahora quiero dejar a John con la palabra, y yo creo que la principal pregunta que quiero responder en la presentación de John es ¿cuál es el nexo, cuál es la relación entre la incertidumbre que tenemos en los resultados de un modelo, sea paramétrica o estructural, y el uso que le queremos dar a los resultados del modelo para la toma de decisiones? Así que John, I leave you now with the screen. Gracias por su atención.
Okay, now I will try to show my screen. Share and then. So, are you seeing my screen properly?
Yes, John.
Okay, good. Get this laser pointer working. Okay, so thank you, Paulo. And what I'm going to say echoes in a lot of ways what Paulo said. So I'm just going to share for the next 3/4 of an hour or so my thoughts on decision support modeling. And they're a little bit different from a lot of other people, and that kind of reflects the journey I've taken coming from geophysics, where data assimilation and parameter estimation is everything. In groundwater, we tend to think we can simulate what happens under the ground. I'm not so sure that's the case. And to the extent we believe that, this may actually compromise our ability to use models to support decisions. And in the end, that's why we model. We don't model to simulate what's under the ground. We model to help someone make a decision. And if we forget that, we may get this whole modeling thing wrong. Modeling may not live up to its potential. I think modeling has enormous potential in helping us to support decisions. I don't think that potential is being realized yet in everyday modeling practice. So before I start off, I'll just say a few words about GMDSI. The last few years of my life, I've been involved in Groundwater Modeling Decision Support Initiative. This is an industry-funded project hosted by Flinders University. And if anyone is interested in obtaining free educational material, free software and webinars and tutorials, it can all be downloaded from this website. So this is a pretty good research if people are interested in the sort of ideas that I'm going to talk about now and how to implement them. So I start off with a very old example, which some of you have already seen. This was done by a student of mine about 30 years ago. But this is kind of one of those times, one of those incidents in life that really changed the way I think about modeling. So we've got a model grid. It's just a rectangular grid. A particle flows through a heterogeneous field of hydraulic conductivity down to the bottom of the system. That's how long it takes, that many days. Now I'm going to calibrate this model against heads generated with that same stochastic field. But I'm going to make that same prediction with a perfectly calibrated model. I'm entitled, in this case, to calibrate perfectly against those heads because I generated them with the same model and with the truth reality hydraulic conductivity field. That's what I get out of the calibration process, a pale reflection of reality with some of the features of reality, but that's as much as I can get out of 12 heads. When I make my prediction with my perfectly calibrated model, that prediction is 100% wrong. So what does this tell me? Well, a couple of things. Firstly, on the mathematical side, it's wrong because there are a million ways to fit 12 heads with very different parameter fields that express detail that's well beyond the reach of the calibration process. The other thing that's important here is the philosophical thing. Is that model that I just built or my student just built a bad model because it doesn't give the right answer? No, there's no mathematical reason why it should give the right answer. A model is bad when the right answer doesn't lie within the uncertainty limits that modeling gives me the ability to quantify. So this model is actually a good model. When I quantify uncertainty, the right answer does lie within the uncertainty limits. Uncertainty is broad because of the high degree of non-uniqueness. So this tells us a lot about modeling, because the real world is going to be a lot more complicated than these synthetic parameter fields, and in the real world we'll probably have a lot less data. So groundwater modeling as it is often done at the moment. So whatever country you go to, there's advice that people provide, normally in the form of guidelines. In Australia, we have the Australian Groundwater Modelling Guidelines. Any modelling done in this country, the contract you sign, you have to abide by these guidelines. Now, and the guidelines here are very similar to the guidelines elsewhere. Guidelines in other countries often refer to these guidelines. Now, the good things about guidelines is, well, it's public discussion about what comprises good and bad modeling. There's a lot of good practical advice in these guidelines. But in my opinion, there is one or two serious flaws which undo all the good that these guidelines do. And the same applies in other countries as well. What's missing here is the metrics by which good and bad modeling should be judged. And if we don't know those metrics, then our ability to make decisions as to how we build an individual model has no reference point. And for reasons I'll talk about, building a model to address a decision support problem is one subjective decision after another, and each one of them must have a reference point. Each one of them must refer to a metric about what comprises a good and bad model. They are missing from documents such as this. Therefore, there's a default metric, an unstated metric, and that metric is integrity of simulation. The idea that if we make our model complicated enough and put in enough detail and fit data well enough, the asymptote of all that complexity is something approaching reality. Nothing could be further from the truth. Integrity of simulation is something we'll never have, in my opinion. Integrity of simulation should absolutely not be the de facto metric by which modeling is judged, because that takes us onto a side road. The main road here, the main game, is supporting decisions. Does integrity of simulation support decisions? Well, not necessarily. If we could, in fact, achieve integrity of simulation, maybe it would, but we never can, and the guidelines need to reflect the fact that we never can, so that decision support modeling can live up to its potential. So let's look at these issues and try to create a chain of logic that allows us to live in a world where decision support modeling can be useful while being very imperfect. The two do not contradict each other if we recognize that groundwater modeling will always be imperfect. So, why do we model? Well, we want to make predictions. And we apply, as Paulo said, these partial differential equations. We, in our wisdom, know what water's going to do before water knows what it's going to do itself. We've captured the behavior of water in these elegant equations. But there's one problem. That's the coefficients in these equations, the hydraulic properties of the medium through which water flows. How little we know about them. In fact, I don't think there's one field of science or engineering where such elegant equations are applied to media whose properties we know so little about. And that has to be taken into account. So another issue is, as Paulo pointed out, do those equations even apply? These apply on a micro scale, at the scale where differentials apply, so-called representative elementary volumes. Within a model grid cell, so much happens that do those equations, when they're converted to matrix equations, even apply? Well, up to a point, but not exactly. And then there's the media through which groundwater flows. It is a mess. Many geological processes superimposed on each other, and then weathering, and then all the other, and then structure. Can we actually provide the coefficients that relate to media like these? Of course we can't. The best we can do is to give these a probabilistic representation. But even that is overstating our ability. Can we give a probabilistic, a stochastic representation to a mess like this or this or this? Everything we do is going to be approximate, but it will be probabilistic. If we're going to apply modeling properly, the first thing we have to realize is that our knowledge as it pertains to a particular study site as encapsulated in those coefficients that we use in the partial differential equations that are encapsulated in models, our knowledge as it pertains to them is stochastic. We don't know what's under the ground, but we know what's not under the ground. In that uncertainty limits, there's a wide range. Any parameters we give a model must have a probabilistic description. Any predictions we make with a model must have a probabilistic description. So, okay, once we recognize that, we can start to talk about metrics. And we need those metrics if we're going to judge our own models, if we're going to judge the models of others. Now, the metrics ultimately have to refer back to the job of what groundwater modeling is all about. Why are we doing groundwater models? To help people make decisions. There's a whole theory of decision making, but ultimately, most decisions come back to one simple question: if I do this, what can go wrong? If modeling doesn't address what can go wrong, it's not supporting decisions. So we know that any predictions made by a model are going to be probabilistic in nature. The job of modeling is to say what is the statistical difference between something bad that may happen and predictions made by the model. Now, this actually, the fact that we're always working in the shadow of something we don't want to happen means that whenever we do decision support modeling, we've kind of got a hypothesis. And this has overtones of the scientific method. And that's good, because after all, our job is to give scientific credibility to the decision-making process. And the scientific method requires a hypothesis. Now, remember how the scientific method goes. You can reject a hypothesis. You can never accept a hypothesis. The scientific method said there's an asymmetry in our knowledge. You can reject, but you can't accept. But for the moment, the nice thing is that the decision-making context comes with a ready-made hypothesis. That is, that something bad is going to happen. Our task in being scientists and using modeling as a scientific instrument is to see whether the hypothesis that something bad is going to happen can be rejected on the basis of the knowledge we have at the moment. Modeling will allow us to reject a hypothesis if it can demonstrate incompatibility with the behavior of the system and the measurements of system behavior. So, we're coming from a scientific background to look at these metrics, as we must, because that's our job, to lend scientific credibility to the decision-making process. Now, just like the scientific method says, we can only reject, we cannot accept. There's an asymmetry to knowledge. I think there's an asymmetry to the metrics that we must apply to groundwater modeling. There is no success, but there is failure. And what is failure? Failure is if we build a model and we reject the hypothesis that a bad thing will happen, but it actually can happen, then that's a false rejection. That is failure. So this is the thing that we must always steer clear of. Any model we build, we must guarantee the client, the stakeholder, the regulator, that if we reject a hypothesis, it stays rejected. If we're wrong, that is failure. At the other end of the spectrum is uselessness. So there sure is one way to make sure that I never reject a hypothesis, and that is to make my uncertainty interval so broad that I don't reject any hypothesis. Well, thanks a lot. That doesn't help much. That's not making use of data or information contained in data. So for me, in groundwater modeling, there is no success, but that doesn't stop us having metrics, and those metrics are failure and being useless. We've got to sit somewhere in here. Where we sit is going to be a subjective decision. It's not going to be satisfactory. There'll never be a model that you can build that you can stand back and look at like you've just formulated the statue of David and say, what a wonderful work of art. No model's ever going to be like that. It's going to be a succession of compromises. But we have to choose our compromises to put ourselves somewhere in here to avoid failure, to avoid uselessness. There is a presumption in the current guidelines, as they're stated, that if we make our model complicated enough, if we worship the gods of partial differential equations in an impossibly complex model, then we get a get out of jail free card and we'll somehow land here in the middle of this spectrum. There is no scientific justification for that proposition, even though it is the unstated metric behind most guidelines. Yes, we have to put ourselves somewhere along this spectrum, but we have to choose our place. We have to own the decision of where we choose. We've got to make compromises to decide whether we're going to be here or here, and we have to make each one of these decisions in light of these two metrics which guide our behavior, now that they're out in the open, now that they're defined. And everything is going to be a compromise. And what's a compromise? It means we're going to do something wrong. It means the model may incur some error as a result of my compromise. And what is error in modeling? It's bias. Bias can be defined in a number of ways. Perhaps the most salient way is uncertainty that you can't quantify. Whenever I make a compromise, there's a possibility of error in my model. I can't help but make compromises. Errors will be incurred. Somehow or other, I have to include in my uncertainty intervals the propensity for error that I incur when I make a compromise. There's no way of getting around this. We're not going to know exactly that propensity for error. We have to guess it, judge it. But we have to know a lot more about modeling than just partial differential equations. We've got to know what the costs and benefits of different compromises are so we can place ourselves on this spectrum. Let nobody expect that integrity of simulation will be the outcome of these compromises. What they have a right to expect is best possible support for the making of decisions. So decision support modeling then is like filling in a ledger. That whenever I make a compromise, for example, I might decide to make the model a little bit simpler. Well, a bit of simplicity may incur bias, but the model may run faster. It may be more stable. I can history match better, assimilate data. I can quantify uncertainty better, reduce uncertainty better. But the cost is a little bit of bias, which I hopefully include in the uncertainty intervals. Every decision we make implies a ledger. Our job as decision support modelers, our job in judging decision support modeling is to know how to fill the elements of this ledger. And the elements of this ledger are missing from just about every groundwater modeling standard that I know of. Yet they are probably the most important components of groundwater modeling. So let's have a look at sources of bias. So to do that, we've got to take modeling and decompose it into its building blocks. The model has two fundamental building blocks, structure and parameters. The structure is kind of like the grid, the layering, the things which allow us to turn differential equations into matrix equations. The parameters are the coefficients in those equations. Ideally, a parameter should be defined as anything that's adjustable. Why do I want to adjust stuff? I want to adjust things when I history match. That's harvesting information from data. I want to adjust stuff. I want to wiggle stuff when I want to quantify the repercussions of lack of data, uncertainty. Anything I don't know should be adjustable. Anything I know should be rigid. Unfortunately, even though these are the fundamental building blocks of a model, we can't really decompose them into stuff that I know and stuff that I don't, because I don't really know the layering here. There'll be a lot of things hardwired into a model that I don't really know. Not everything that I don't know can therefore be a parameter, and that causes problems. That's why we need compromises. Ideally, what I don't know should be wiggleable, adjustable. What I do should be rigid. They're the fundamental building blocks of a model, but I cannot decompose my knowledge on lack of knowledge in accordance with those building blocks. That's one of the reasons why compromise is always necessary in groundwater modeling. So let's look at some of these the sources of bias, so that we can then be in a position to choose the compromise that's best for us in a particular decision support modeling context. I'm going to have structural complexity on the x-axis, parameterization complexity on the y-axis. Now, most models, I'll just point out, seem to sit here. People like to have a structurally complex model. They drape over a simplistic parameterization scheme. In my opinion, this is about the worst place to be on this graph, but it's the place that most models sit, often with reference back to guidelines as to why they're ending up here. So let's look at some of the compromises. If we make our model structurally simple, well, we all know what can happen there. It can be too simple to represent the processes that it's meant to. It can incur errors through omitting things, through a grid that's too coarse. Many things can go wrong if the model's just too structurally simple. For models too structurally complex, things go wrong there too. Structural complexity implies I'm hardwiring in to the model a lot of things that I don't know. Anything that I hardwire that I don't know is a potential source of bias. And in addition to that, structurally complex models run slowly. They're numerically unstable. I can't do history matching well. I can't harvest information from data. I can't quantify uncertainty, which is the repercussions of insufficiency of data. There's compromises here then. What if my parameterization scheme is too simple? Now looking at the y-axis. If I have a simple parameterization scheme, it compromises history matching. Or it means that if I have data over here and I've got a big zone of piecewise constancy and use the data here to imply the properties here, well, I've hardwired in bias and I don't have the ability to quantify lack of knowledge if my parameterization is too coarse. But having a very complex parameterization doesn't get over all these problems. If I've got a complex parameterization, then I need to have a prior probability distribution to match the parameterization complexity. When I history match, that prior probability distribution is like a traffic policeman. It directs the information that I obtained from data to the first layer, the second layer, the third layer of the model. If hydraulic gradients are flat, where is the high K? Which layer? The prior probability distribution tells me that. But the more complex, the more layers I've got, the greater the complexity, the more parameters, there is confusion as to where information flows into that model as I history match. So there's just as much a propensity for predictive bias through over-complex parameterization as through under-complex through simplistic parameterization. Everywhere I turn is a source of bias. Well, that's okay. That's the nature of modeling. That's why there can be no perfection. That's why there must be compromises. That's why we've got to seek the right balance. And it will always be a balancing act, and it will always be subjective. And we're not getting enough guidance on how to do this in current guidelines. Well, where do we get this guidance from then? Well, there's three sources, many sources, but there's three principal sources which I'll touch on briefly. Again, rarely mentioned in guidance documents. The first is Bayes' equation. Most of you would be familiar with Bayes' equation. You start off with a prior probability distribution of parameters. This is kind of your mental image, your stochastic representation of your site knowledge, images of what's under the ground that you can conjure up, the earth and all its beautiful complexity. But not any image of the subsurface, not any realization that you can conjure up in your imagination really should go into the model, because a fundamental prerequisite for predicting the future is that you match the past. So we have a likelihood function, which is kind of a filter function. And then any parameter, any realization of the prior probability distribution, which by definition satisfies your expert knowledge, which allows the model to replicate the past, can be used to make a prediction, and that's called the posterior probability distribution of the prediction. Probabilistic to start with, probabilistic to finish with, and then we can judge the statistical distance between the model prediction and the bad thing. So Bayes' equation is just common sense, really. Easy to write, difficult to implement. Bayes' equation suggests that, well, parameterization and structural complexity are what we need to do. We need to express all the details of our expert knowledge, even though it's probabilistic. And the more parameters we have, the more information we can harvest from data, the more we can quantify the repercussions of lack of data. Bayes' equation suggests that this is where we should place ourselves on our little map of complexity. This is kind of the holy grail, if you like. However, to follow the precepts of Bayes' equation, and Bayes' equation alone, will get us into untold trouble. This is the right place to be if the model structure is correct in every way, if the prior probability distribution is correct, which it never will be, if we can, everything we don't know is adjustable, and if the model allows them to be adjustable by running fast and being stable, yeah, this is the right place to be, in theory. This is the kind of beacon on the hill, as I say, the Holy Grail. In practice, we're not going to be here, but it's good to have a reference point. In practice, there are compromises, there's a ledger. The second source of inspiration, singular value decomposition. Now, this is a concept of linear algebra I'll just mention briefly, but it's all based on subspaces. And I think we do not, this linear algebra, and I don't want to bore people with the maths just a little bit, but the inspiration to be gained from singular value decomposition is enormous, because when we're building a model, we're decomposing a problem. And the mathematical path, the road less traveled, is in singular value decomposition. This equation here says that what we observe in the field, which I'm representing as a vector, is the action of the model, which I'm representing as a matrix, on parameters plus measurement noise. What we observe is the action of the model on the parameters plus measurement noise. We don't know the parameters, but we do have observations and we can guess noise, and we've got Z matrix. That's our model. I've linearized it. I'm replacing the model with a matrix. This is a sensitivity matrix. A lot of you are familiar with the sensitivity matrix. Now, I can do singular value decomposition on that singular matrix, and that gives me three beautiful matrices with special properties. The one I'm most interested in is this V matrix. All its columns are orthogonal. This is a new set of axes in parameter space. These vectors span parameter space. Singular value decomposition allows me to divide parameter space into two subspaces. That which I can estimate, that which I can't. This is huge. This is what the information in the calibration data set tells me. This is stuff that I can only know probabilistically. So, singular value decomposition tells us more. Suppose I've got a three-dimensional parameter space. Singular value decomposition allows me to define new axes, the solution space, the null space. This is the stuff I do not know. I'm going to pretend that I've got a one-dimensional null space and that I have the capacity to estimate two things, two combinations of parameters. Singular value decomposition tells me that the most I can ever know about reality is not reality itself, that K vector, but a pale projection of reality onto a much smaller subspace. Like this. This is a projection of this onto this. Now I go and make a prediction with my calibrated model, just as we did before. That prediction has two terms. The first is that which is informed by the past behavior of the system. The second encapsulates the repercussions of not having enough information. Singular value decomposition gives me my mission statement as a groundwater modeler. Make a prediction, use these two terms. Harvest the information you can, take it into the future. But express, when you're making predictions about the future, what you don't know and express it probabilistically. My job statement as a decision support modeler is to calculate the machine learning term, however I do it, singular value decomposition doesn't say how, calculate the machine learning term, make an unbiased prediction, and make sure you accompany with it uncertainty, doesn't say how, but keep those two terms orthogonal. That's something else that decision support modeling says. Why? Why do we have to keep them orthogonal? Suppose we have a 2-parameter model instead of a 3-parameter model. I can fit this data perfectly with a 2-parameter model because I've got a 2-dimensional solution space. I can get the right projection onto the solution space. But in doing so with my simplistic model, whose parameters are not quite aligned in the directions in parameter space that singular value decomposition would tell me, I incur unwittingly a projection onto the null space. That is bias. Singular value decomposition tells me that the moment that my model is imperfect, the very act of trying to make it more perfect by history matching can actually incur errors, the opposite of what I want to happen. Now, it all starts to get complicated here, so I won't go into the details. But here are the consequences. History matching of an imperfect model runs the risk of incurring predictive bias. However, that bias is prediction specific. For some predictions, history matching is good, regardless of the damage it does to the parameters. If a prediction is pretty much entirely dependent on what happened in the past, if the machine learning term is the only term, the need to have the other term orthogonal to it disappears because there is no other term. However, for other predictions made by that same model, there may be bias incurred by the very act of trying to reduce uncertainty. I may create uncertainty by trying to reduce it. And it's all prediction specific. The link between good parameters and good predictions is broken. Integrity of simulation is not a consideration here. We've lost that the moment we built the model because no model is perfect. Compromises have to be made, and those compromises will be prediction specific. When I build a decision support model, it must be designed, built, and history matched with a specific prediction in mind. There's no such thing as integrity of simulation, which is good for all predictions. Okay, that's good. I know that now. So that's an important concept. If there's two things that matter, I may have to build two different models, each tuned to the making of that prediction with uncertainty quantified, information harvested, bias reduced. And I can only do that if I do it in a prediction-specific manner. So finally, insights from pessimism. Do we have to know the entirety of the posterior probability distribution of parameters? No. And of a prediction? No. Normally, we're only interested in the pessimistic end of the posterior probability of a prediction. And in so many cases, the pessimistic end of a posterior predictive probability distribution is going to be dominated by one or two or just a handful of things. Is there a fault or is there not? What's the throw of that fault? What's its length? Does it abut two layers that may then move water from one stratigraphic unit to another? Often as not, the things that affect the pessimistic end of a prediction we care about can be decomposed into a few fundamental things that we need to get right. Well, we're never going to get them right, but we need to be able to simulate their existence or their non-existence in a way that allows me to make bias-free predictions and quantify what I don't know. And that means that in so many cases, we can focus on what matters and dispense with what doesn't matter. Modeling becomes easier, directed, prediction-specific as it must be, less costly, more effective, and more closely aligned with the imperatives of decision support modeling, the metrics that we spoke about earlier. So, it's all about the ledger. So where do we go? What are some of the options we can use here? How do we get away from this dreadful place to better places on this map? So just 3 examples. This at this end of the map is software called Pastas. This is written by Dutch colleagues of mine, and this can be used where a prediction is pretty much entirely solution space dependent, where what happens in the future is pretty much informed by what happened in the past. Pastas says forget about the big model in that case. All we need are signals. Signals, this is all about signal processing. We can parameterize the signals that applied in the past, carry them onto the future, make accurate predictions, and quantify their uncertainty. If we're in a situation where the past is the key to the future, this is all the complexity we need. It's just machine learning, and the model or the device that we build for machine learning is optimized for that task. So this may be the proper decision support modeling response in some circumstances. It's fast, effortless, and it's good, but doesn't probe the null space. So we can't use this where there's lack of data, only where there's lots of data. Now, here's a case that actually is one that I've encountered quite a bit in the area that I work. Often models are built, or they try to be built, that sit here on the map. In my opinion, most of these are abject failures. Can we do better by decomposing the problem? So we've got a situation here where someone wants to put in a coal mine. We've got a coal seam here, and regulators are worried that this coal mine, because water is going to flow into that mine, may impact river flow here. It may also impact recharge into an aquifer, a deep aquifer, possibly because of faults, which may or may not exist here. Now, this is often the subject of proposals to granting an application for mining. The knee-jerk reaction is build a big, complex model, because regulators are worried that unless a big, complex model is built, they're not doing their job in making the proponent build a big, complex model. That means they don't care enough unless this model's complex enough. Now, that's not scientific, but that's what happens just about every time. So we try to build a complex model. We've got 2 systems here, the surface system, the deep system. They interact. It's complex, yes. Therefore, a complex model is required. But a complex model will be slow running, difficult to construct, and it'll have numerical issues. This interaction of these 2 systems will have numerical issues. For example, consider the interface between these 2 systems. Well, how much water flows from the regolith down to this deep aquifer is determined by the ability of this deep aquifer to accept it. As soon as we try to simulate this numerically, we got problems, even though modern unstructured grids allow us to abut subcropping layers against a regolith layer, there's little issues surrounding discretization. Now, these can be overcome, but it's just getting more and more and more complicated. And what I see time and time again is that someone starts off with one problem, that is an environmental problem, and they end up with two problems, the second problem being the model, and trying to make this model look respectable often gets in the way of actually solving the first problem. There's another numerical problem. What happens close to the pit? If I simulate this as an unconfined system, as I should, water levels the saturated thickness can get very thin close to the pit, and this has an effect on how much water flows into the pit, and that has an effect on impact. If I get this wrong, I can get everything wrong. I've got to make sure I over-predict rather than under-predict. Building a complex model makes it almost impossible to compromise. And compromises, as I said before, is how this whole thing is going to work. So what's plan B? Plan B is to decompose the problem. There's not much data here. Can I decompose this problem in a way that actually gives me access to a lot of data? And what is that data? So let's say, by decomposing the problem, there's two impact paths, the superficial one, the deep one. Let's assume that the KH, the hydraulic conductivity in the regolith, is much greater than deeper down. That's always, well, in this case, that's a pretty good assumption. If that's the case, let's look at each of these impact pathways separately. So let me assume then, I'm going to build a steady state model. I'm going to assume this superficial aquifer is reasonably independent of the deep one. I'm also going to assume that transmissivity does not vary with saturated thickness, so pseudo-confined, though confined is the wrong word. That way I don't underpredict inflow to the pit. Now let me recognize the fact that basement's only, going to be about 30 to 40 meters deep. The water table will be about 20 to 30 meters deep under the hills and closer to the surface in the valleys. What I just said is huge. It means I can use topography to calibrate this superficial aquifer. I can say groundwater flows roughly parallel to the topography sitting on the basement, and suddenly I have a calibrated observed value of topography in every cell that I can back calculate transmissivity with. It's going to be uncertain. Of course it's going to be uncertain. I can quantify the uncertainty. The model runs like the wind and it's got thousands of data points for calibration. Therefore, I can estimate transmissivity. Therefore, I can estimate superficial impact with uncertainty, which I can quantify. So these are maps done by a colleague of mine. These are the proposed coal mines. He knows recharge pretty well throughout this model domain. There are his calibration targets, the flow directions, calibrated groundwater level, calibrated depth to water. There's the prize. There's the calibrated transmissivity field. He's in a position now where he can calculate superficial impact. The deeper system, we know so little. But what matters? Whether this fault exists or not, and possibly the ability of this aquifer to induce a bit of recharge from the superficial system. Get rid of everything we don't need. 2 layers, simple boundary condition, and we've got our second model, which we can use to quantify the large amounts of uncertainty that exist here, mostly governed by the existence or otherwise of this fault. Suddenly, the problem's tractable by not going down the path of integrity assimilation, because we're never going to get integrity assimilation, but by going down this path, we've actually solved the problem. Finally, what if we got a situation which is unavoidably complex and we have to sit here? It's decided we can't sacrifice structural complexity. We can't sacrifice parameterization complexity. Well, we can live with that too if we take compromises. And that compromise is data space inversion. So we can generate realizations of our prior of arbitrary complexity. Run the model as complex as we like, 300 times and only 300 times. run it over the past, run it into the future, and we can look at the prior uncertainty of a prediction we care about. Now let's bring our observations into play. We have measurements of what this system did in the past. There are the observations. There are the model-generated counterparts to the observations. Now let's throw the model away. Let's throw the observations away just for a moment. We've run the model over the past, run it into the future. We can build up a empirical covariance matrix that links the past to the future. The equations are simple. We learned them all back at high school. Once we've built this covariance matrix based on 300 runs of the complex model, we can build a very simple surrogate model based on that covariance matrix. Now we can bring our data back into play. We don't calibrate the big complex model because it's uncalibratable. We don't actually adjust parameters because there's no need to. We say we've already got our linkages between the past and the future. We calibrate the surrogate model to obtain the posterior probability distribution of a prediction that we're interested in. There's compromises here. There's a little bit of a Gaussian assumption here, which we have to live with. Yes, we made a compromise, but we've occupied a space where we're structurally complex, parametrically complex, and satisfied the imperatives of decision support modeling, made hopefully a relatively bias-free prediction and quantified its uncertainty. And with a little bit of extra work, we can even look at the worth of data that we haven't even acquired to see how much uncertainty would be reduced through, for example, a monitoring network or the acquisition of extra data. So it's all about compromises. The compromise has to be prediction specific. There is technology and tools available. Our job is to decide what compromise is most appropriate in what place, and then placing ourselves on that spectrum between failure and useless, but in a position we choose to be rather than landing in a random place by feeble attempts at integrity of simulation. So, how should we view decision support groundwater modeling? Integrity of simulation or integrity of predictive uncertainty? Getting the flow of water right or getting the flow of information right? Creating a digital replica of the subsurface or implementing the scientific method? Well, it's obvious, isn't it? The guidelines, they don't explicitly, but implicitly, they tell us this is the way to go. Logic, science tells us this is the way to go, but we've got to know how to fill in the elements of this ledger. We'll never get all these right, but that doesn't mean we can't implement the scientific method. That doesn't mean we can't get these right. It is not dependent on getting these right. Nothing will be perfect. Probably the most imperfect thing will be to go this path rather than this path. So, coming back to the real world and the situation that regulators often face, suppose we want to use a resource here and ask what is the impact here. Suppose there's a threshold. Do not let the water level fall below this threshold. So, suppose we've done everything that I've just been talking about and the proponent has got a modeler, engaged a modeler. They've tested the hypothesis that the water level will fall below this threshold if the resource is developed, and that hypothesis can be rejected. What are the job statements here? The regulator's job is not to say, or have you done everything by the guidelines? The regulator's job is to say, satisfy me that your rejection of that hypothesis is truly a rejection, that you haven't committed a type 2 statistical error. The proponent's job is to convince the regulator and society that this hypothesis is safely rejected. That's the job. What about we do modeling and we show that it's quite possible that something bad's going to happen here? Well, then the job statements become different. The regulator's got to thank the proponent for his or her honesty, and the proponent needs to write an invoice and console the client. Most times it's going to be line ball. There's one thing about uncertainty and groundwater modeling. Seek and you will find. There's uncertainty everywhere. We can't reject every proposal on the basis that we can't reject a hypothesis that something bad may happen, because that hypothesis will almost never be rejected. But we can't say all development must cease. And this is difficult territory, and no one wants to be here, but this is where we are, and we have to live with it and learn how to live with it and learn how to use groundwater modeling to teach us how to live with it. In this case, maybe a proponent will be granted the ability to mine, provided adaptive management is followed, provided that a monitoring network is put in place, and provided that operations will change or even cease if certain monitoring thresholds are crossed. So there's a new proposal, a new hypothesis. The hypothesis that we now must reject is that the threshold will be crossed if the hypothesis that we must test and see if we can reject is that the asset can be safeguarded if certain courses of action are taken once certain monitoring thresholds are crossed. This is a more difficult hypothesis to test, but it's the one that we're always going to have. So modeling does not stop with the proposal. Modeling has just begun. Modeling must tell us where is the place to gather the most data to give us the earliest warning that something may go wrong. We just talked about how this uncertainty analysis can be used to support the acquisition of further data. There's a new hypothesis. The proponent must convince the regulator that the hypothesis that adaptive management won't work can be rejected. So it's still the scientific method, it's still modeling, it's still following the metrics that I've just talked about, but in a slightly more sophisticated way, or ongoing modeling, monitoring, assimilation of data acquired through optimal monitoring improves the predictive ability, quantifies uncertainty, modifies uncertainty as the system responds to the proposal, and readjusts its assessment of uncertainty on each occasion that data assimilation takes place and uncertainty is requantified. But the type of modeling required to do this will be very much tuned to the assimilation of data that is pertinent to the prediction that we care about, which is this one, and all the things that I just said about the best way to do that apply. So what do we need? We need stuff that the guidelines aren't giving us. Philosophical link between modeling and the scientific method. The specification of the need for prediction-specific compromises. How to make those compromises, but mostly metrics by which we can judge the efficacy or otherwise of those compromises, and rejection of the proposal that integrity of simulation is the metric for decision support modeling. It is not. It's the ability to support decisions, and for all the reasons I've just spoken about, that's going to involve compromises and approach to groundwater modeling, which has integrity of simulation not as its primary goal, but integrity of decision support as its primary goal. Which means we've got to know the entries on this ledger better than we do now and need a whole lot of advice on what they are, and then we can move forward to better support the decision support imperatives. Okay, and with that, I conclude.
Thank you very much, John. So I think now we open the floor for questions. Paulo, no sé si me imagino para cualquiera de los dos exponentes, digamos. So anyone willing to ask something? I'm a lawyer, so I don't dare to even comment anything of what you just said. I try to understand broad lines, but I leave the floor for the engineers. Sorry, I have some spice
That's
here.
fine. Well, as a lawyer, the only advice I can give you is treat anything a groundwater modeler says, take it with a grain of salt.
Good. Well, I will.
No one has any questions.
Yes.
So I've either done a
Yeah.
very good job or a very terrible job, Paulo.
Very good one, I think. I would like just to make some comments in Spanish, John, but it's mainly to reflect on your presentation. Yo creo que algo bien importante, como les decía, como le comentaba yo, me he encontrado con John en varias otras oportunidades, he tenido tiempo de pensar un poco estos temas. Yo sé que es un tema a veces un poco complejo, que la matemática algunas veces puede intimidar un poco cuando uno lo ve por primera vez, pero creo que es un tema bien relevante en la práctica. Y una de las cosas que yo creo que John puede aportar mucho es con su participación en este proyecto de Decision Support, en el cual están viendo cómo aplicar esta idea a problemas reales, digamos, principalmente asociados al mundo de la minería en Australia y en otros países. Así que yo creo que es una buena oportunidad para la gente que trabaja en esos temas de poder también tal vez simplemente comentar su experiencia con el uso de modelos para este tipo de proyectos y para la toma de decisiones.
Solo comentando lo que dice Paulo, efectivamente, o sea, yo, más allá de mi poco expertise técnico y más bien jurídico, estas herramientas son las herramientas con las que hoy día se maneja la evaluación ambiental de proyectos, por ejemplo, los impactos respecto del agua. Tanto manejar estos conceptos y estos niveles de incertidumbre respecto de estos instrumentos es fundamental para entender y para hacer una buena evaluación al final del día. Hay una consulta. No hay inconveniente si quieren hacer la pregunta en castellano y la traduzco yo o Paulo eventualmente la corrige si es que hay alguna cosa que traduzca mal, digamos, pero es muy técnica. Pero adelante, Javier.
Hola, buenas tardes. Sí, gracias por la oportunidad de consultar. Yo quería hacer una nota en español quizás primero y después remitir la pregunta a John, porque me parece que el mensaje que se está generando a partir del uso de modelos tiene implicancias que son mucho más contundentes para el diseño y uso de modelos, sino que incluso alcanzan, creo que tal como lo mencionaste tú, Carlos, al método, ¿cierto?, que hoy día se usa para evaluar estudios de impacto ambiental. ¿Ya? Esto tiene, creo, repercusiones que son mucho más relevantes. Y puedo hacerle la pregunta a John en inglés. Nosotros hemos trabajado junto con John y nos conocemos bastante, pero creo que este tema no lo hemos hablado a lo mejor en ese detalle. ¿Ya? Y lo que John está planteando acá es que ningún modelo, ¿cierto? Si uno es riguroso en incorporar todas las fuentes de incertidumbre que existen, prácticamente ningún modelo va a poder demostrar, ¿cierto?, que algún umbral ambiental no se va a superar, ¿cierto? Si nosotros incorporamos fuentes de incertidumbre y las analizamos todas, probablemente vamos a obtener una probabilidad de distribución que sí pasa ese umbral y que por lo tanto, bajo la métrica estándar y clásica de los análisis de impacto ambiental, ese estudio de impacto ambiental va a tener que rechazarse porque hay probabilidades de que ese umbral se sobrepase. Sin embargo, ¿cierto? Si nosotros usamos los modelos para definir eso, sí pueden darnos luces de cuáles deberían ser las medidas de un plan de alerta temprana, ¿cierto? O las medidas el diseño de un plan de alerta temprana que diga, estamos viendo, ¿cierto?, que aparentemente el umbral se está acercando y probablemente nos estamos ubicando cerca de esa predicción que hizo el modelo, cerca de esa cola de la distribución de probabilidad, y por lo tanto tenemos que tomar estas medidas. Y eso sería un uso mucho más sensato, ¿cierto?, y más razonable de los modelos, porque de otra forma terminaríamos probablemente rechazando todos los estudios de impacto ambiental porque siempre vamos a poder encontrar la forma de meter incertidumbre en un modelo y encontrar cómo se sobrepasa el umbral que estamos tratando de proteger. Creo que eso, digamos, es un planteamiento para una discusión. No sé si quieren que a lo mejor yo le traduzca la pregunta a John o Carlos, si tú puedes, digamos, hacer un resumen quizás más sintético.
What Javier said, John, if I got it right, is that models, hydrological models, are being taken in the Chilean environmental assessment as tools to predict impact assessment, and sometimes the authority is taking the models as exact tools or intends to obtain from the model a precise data or a precise parameter, trying always to avoid uncertainty. Correct me, Jaime, if I'm not getting it right, but what you're saying is that the model is a tool that contains a percentage of uncertainty, and if we are not understanding that right, and the authority sometimes is asking the model something the model is not able to deliver. Therefore, we are speaking almost in different languages here between what the model can deliver and what the authority is looking for in environmental assessment. Something like that, Jaime, probably?
Yeah, Carlos, it's basically that what just said at the end of the presentation is that if you incorporate all the uncertainty that you can gather in a model, if you account for all the sources of uncertainty, you will probably find a probability distribution where the environmental threshold is going to be surpassed in every project. So if we go in that route and we use the classical approach to impact assessment, then all the projects will be rejected. But what John is saying here is that the models can be used and should be used to properly design early alert plans and properly design the identification on when the system is going to that path, right? So it's not that we're gonna estimate uncertainty and say that thing will never happen. It's that we're gonna estimate what is uncertainty and define with that uncertainty when that threshold can be surpassed and how to design the early alert plans for that not to happen. So I guess maybe if John can comment on that, because it is huge when we have the ability to estimate uncertainty. Having so many sources of uncertainty, we will always find a way, and the regulators can always make us find a way that the project is going to fail.
I think this is true. I think recognizing that there's always going to be uncertainty requires more sophistication than we have at the moment. Now, mathematically, numerically, we are acquiring that sophistication. The next thing is for society to acquire that sophistication. In a world where everything is so contentious, everyone wants to keep little secrets if there's a risk. And in some ways, you can't blame them. So don't be alarmed, the risk isn't that much. But people will be alarmed because at the moment, we all get alarmed about everything. But we need to be, I think, have a level of societal sophistication that matches the mathematical sophistication, so we can choose the risks that we're going to take, knowing that they're risks and knowing that we have the ability to minimize those risks and knowing that we can't avoid taking some risks. But I think society is going in the opposite direction at the moment. But it also means that people like us are going to have to be at the center of risk assessment, and people are going to have to trust us as modelers to be honest about our assessment of those risks, even if they don't quite understand the mathematics behind it. What people tend to want to see now is Groundwater, the movie. Show me the animation that everything will be okay, then I'll believe you. What they don't want to hear is me or RVA or other people saying, it'll be all right, because I've done singular value decomposition here. You don't understand, but trust me, because no one trusts us anymore. So we have a hell of a problem here, and the way forward, well, we can only find a way forward by talking honestly about it.
Okay. Sí, solo para explicarlo en castellano muy sucintamente, que en el fondo la sofisticación a la que han llegado los modelos y los niveles de incertidumbre que tienen, hay que traspasarlos de alguna manera a la sociedad y que la sociedad esté dispuesta a asumir la toma de decisiones con ciertos niveles de incertidumbre. Es decir, que estemos dispuestos a que hay que asumir que hay ciertos riesgos que los puedo descartar, pero que hay otros riesgos que los tengo que asumir si quiero avanzar con el desarrollo de ciertas actividades. Y ese nivel de sofisticación en la sociedad todavía no ha alcanzado. Y más bien uno lo que observa es que la sociedad va en un camino contrario, que la sociedad lo que quiere ver es una especie de película de lo que va a pasar, ¿cierto? Y que va a estar todo perfectamente controlado en circunstancias que sabemos que eso no es así. Entonces, lo que plantea John es un desafío más bien social o comunitario de lograr que la sociedad esté dispuesta a confiar en decisiones tomadas por expertos con riesgo, con la asunción de riesgo y no con certeza. No sé si Paulo quieres complementar algo.
No, acabo de ver que hicieron otra pregunta en el chat que parece bien interesante, dar la oportunidad.
Justamente, iba a pasar eso. Si quieres, hazla tú, dale, adelante.
So, John, someone here is asking in the chat does it make sense to make models to predict levels? Isn't it better to invest in monitoring wells?
We have to invest in monitoring wells, but I don't think we can ever dispense with the need to make some assessment of the repercussions of our actions. So the more wells that you have, the more information you can put into the model. But ultimately, you've got to make a prediction, quantify its uncertainty, and then monitor for sure. And as I just said, if you can quantify uncertainty, you can quantify reduction in uncertainty. Therefore, you can quantify where is the best place to put that monitoring well. So it's not an either or. I think they both go together and both can and must support each other.
Mm-hmm. Yes, I would like to just comment on that I think John have done a very good job in presenting how complex this problem can be. So essentially, we can never be sure about our models or about groundwater models. We can never trust them 100%. However, on the other side, you have that, what are the options? Can we throw a coin and then decide the project goes or the project doesn't go? What do we do with all the data that we gather from the field? Where do we put it? Where can we think about the problem in the way that the models allow us to do. So I think that is a good way to do it, because the other way can be quite frustrating when you're working with models every day. There is another question here. I don't know if you can see that, John. Yes.
Solo para traducir, para quienes no entienden en inglés, la pregunta que tú hiciste es la que hacía Gonzalo en el chat, ¿cierto? Que preguntaba si tiene sentido predecir niveles con modelos en vez de, o no será mejor hacer pozos de monitoreo. Y la respuesta de John, en resumen, es que son dos mundos complementarios, es decir, los pozos de monitoreo sirven para alimentar la información del modelo, pero al final del día siempre habrá que hacer predicciones, ¿cierto? Y tú lo complementaste muy bien diciendo en el fondo que el modelo es también un buen reservorio o receptáculo de la información que se genera con los monitoreos y que te permite analizar, pensar y predecir en el fondo el comportamiento en base a la información que se recolecta. Y el otro punto que hacía John, que también vale la pena destacarlo, es que lo tengo en la punta de la lengua y se me olvidó. Era, em, em, ya me voy a acordar y lo hago. Lo resumo, se me fue. Y
Sorry, Carlos, es que yo planteé el punto porque creo que la autoridad tiene la institucionalidad, para no ser tan específico. Tenemos un punto muy débil respecto al monitoreo, por eso justamente puse el tema, porque yo tengo la sensación, sin dedicarme mucho al tema de la modelación, de que los modelos tienden a ser casi sagrados. En cambio, la información dura que tenemos en Chile creo que no es muy abundante ni muy robusta. Hay muchos pozos de monitoreo que ya no se están monitoreando. Solamente por eso quise poner el tema, aunque entiendo perfectamente que no se puede prescindir.
Perfecto. Había otra pregunta precisamente de Carlos Velázquez y después de eso le damos la palabra a Rodrigo Valdés. La pregunta que hace Carlos es, there is another question, John, in the chat. It's from Carlos Velázquez. He's saying, can you quantify the uncertainty of the predictions of your model? They expect me to tell, it's about clients. Clients ask me, he's saying, can you quantify the uncertainty of the predictions of your model? And they expect me to tell them 10%, 20% or so. See, I see very difficult to quantify the uncertainty due to the uncertainty of each of the many variables of the model use. What will you respond to such questions? That is what Carlos is asking. Carlos está preguntando en el fondo cómo le respondes a un cliente respecto de la incertidumbre de un modelo, que el cliente quiere un porcentaje exacto, ¿cómo le respondes cuál es el nivel de incerteza?
That's a real good question. And you know, the sad answer is that, well, firstly, the answer is no. And secondly, even if I could, you know, what does it mean? There's only one Earth. and it's not as if that if we'd say the chances are 1 in 100, there's an implication there that if I went to another 99 alternate realities, that only 1 in 100 times would failure happen. But we only get one go at this. I don't think we can say, I don't think we can put a number on this at all. However, we don't have to put a number on it. I think in practical cases, we focus on the prediction that matters, the thing that can go wrong, and say, if it goes wrong, this is how it will go wrong. And that will be aligned with how, you know, the hydrogeological conceptual model. And then, in a way, I can transfer responsibility back to someone else. I can say, as a modeler, if it goes wrong, this is how it'll go wrong. Geologists, you tell me how likely it is that these conditions exist. So, and this is something, you know, we've been talking a bit about recently. Should we say, here's the prior probability of Earth properties? I don't think we can do that. Should we say, here's how things can go wrong, you tell me the likelihood or not? But in the meantime, knowing how things will go wrong gives you the ability to monitor in a way to protect you. So it'll always be qualitative, but it should be directed at the thing that can go wrong, so that that's as specific as possible to the decisions we have to make, and arms us with the ability to monitor as strategically as possible. Whether it's 5%, 10%, no one's going to say that. But I think they can say pretty unlikely, and that's about as good as it's going to get.
I just remember some conversations with regulators saying, my model have 5% error, so it's okay. So Paulo, I don't know if you want to comment on that or just
no. I mean, I think one way to think about this is, you know, so groundwater models can be can be complex, and reality can be a lot more complex than what we can model, is to say, what is the main benefit of having a model? What can I gain by setting up a model? So can I do it better than just throwing a coin? Or can I do it better by just guessing, or by just, I don't know, what other methods we can use? And in many cases, I think if we do a reasonably good job on using the data, I think we can get better results with a model than without a model. Now, there is also responsibility of people using the models and building the models to say sometimes, you know what, we cannot answer that question because we have such a huge range of uncertainty that it's really difficult to say. So that is an approach that I think can work in practice. So I'm sorry, John, now I'm going to switch to Spanish because I see there is another interesting question. Hay una pregunta que encuentro que es bien interesante que dice, si quiero hacer simulaciones predictivas por cambio climático, ¿necesariamente debo proyectar recargas? ¿Qué tan certeras podrían ser los resultados? So, John, they are asking about predictions with climate change, about estimating recharge and how much is the uncertainty you can guess for those kind of situations.
Well, I haven't done too much modeling that addresses climate change, just a little bit, and I'm thinking of one at the moment where we did uncertainty analysis. We split that into two parts. The first was the uncertainty pertaining to the properties of the subsurface, and there wasn't much information, and those uncertainties were high. And the second was the uncertainty associated with future rainfall, and the latter dominated. So, of course, I think we've just doubled our uncertainty here. That doesn't make it very satisfying, but I agree with Paulo that we got to consider these things. We have to process the data we have available. And if it's, but you know, there's one really forgiving thing about modeling. Now, the uncertainties will always be large, but models are based on partial differential equations. Just about every time I've quantified uncertainty, and I've also quantified the uncertainty not just of a prediction, but of the change in a prediction. For example, what would the water level be with or without climate change? Now, my ability to say what the water level will be is very small. My ability to quantify the difference in water level is often quantifiably much higher. So that maybe says something about how we use models. If there are predictions that we can make with demonstrably greater integrity, should we not then be basing policy and management on the predictions that can be made with greater integrity, and modeling, having the capacity to quantify uncertainty, has the capacity to quantify uncertainties in differences. And those uncertainties and differences will often be much smaller and perhaps something we can base management and policy better on. So it's just playing to the strengths of modeling here. So as Paulo says, we got a model, we got to assimilate data, we've invested so much in it, but don't expect a crystal ball. But if you use models the right way, you can enhance your ability to make better decisions. But it's using models the right way and what outputs of those models you use on which to base policy or management has a lot to do with that.
Pablo, quizás hacemos un breve resumen en español y pasamos a Rodrigo que tenía la mano levantada.
Sí, no sé si lo quieres hacer tú, Carlos.
Bueno, la pregunta, parto de más atrás, la pregunta de Carlos planteaba cuál es ¿cuál es el número que uno puede entregar respecto a la incertidumbre de un modelo cuando la respuesta a un cliente, ¿cierto?, con tantas variables de incerteza? Entonces, John lo que plantea es prácticamente imposible entregar un número. Lo que sí permite el modelo es, más que entregar un número de cuál es el factor de error, por decirlo así, es decir, es enfocar, el modelo te entrega la posibilidad de determinar cuál es la variable eh, que podría presentar un error o que podría comportarse distinto a lo previsto, o la que tiene el mayor nivel de incerteza, y enfocar ahí la toma de decisiones o el monitoreo, digamos. Entonces, el modelo, más que definir un factor de error, que no es posible por la cantidad de incerteza que tiene, sí permite determinar cuáles son las variables que presentan esa brecha, y eso lo conecto un poquito con lo que planteaba Gonzalo en su pregunta anterior, y era lo que se me había quedado en el tintero, de que en el fondo el, el- la información con la que alimentas el modelo es la que tienes en el fondo, pero la brecha o el nivel de incerteza te permite enfocar el monitoreo. Al final del día tú tomas decisiones respecto del monitoreo sobre la base del nivel de incerteza que presenta el modelo, producto del estudio que se realizó, ¿cierto? Y en relación con el cambio climático, John planteaba que no le ha tocado hacer, si bien no le ha tocado hacer muchas modelaciones, lo que entendí, Pablo, tú me corriges, es que precisamente el trabajo es respecto de la incertidumbre que presenta el modelo sobre las variables a las que se le introduce una componente de cambio climático, y cómo eso permite, en el fondo, eh, mejorar la observación y utilizar el modelo como una herramienta de observación en ese sentido, más que, de nuevo, una bola de cristal que va a predecir un comportamiento específico, ¿cierto?
Eh, ah, sí, yo creo que estoy viendo que hay algunas personas que han salido ya un poco tarde. Tal vez podríamos como resumir, dejarlo acá esto. Ah,
Rodrigo sí tenía su mano levantada, sí,
ah,
no sé si
perdón.
ahora, y después terminamos con Rodrigo y cerramos.
Sí, bien, sí.
Can you hear me? I'm sorry for being the last question. Well, first of all, thank you so much for your presentation, Pablo and John. They were really good. Just talking about uncertainty, you know, most of the uncertainty you are talking about is uncertainty coming off model structure and model parameters, right? But someone was also mentioning that what will happen with the recharge and those predictions to the future. So my question is, let's say we can also have uncertainty propagated from the input data set, right? Let's say if we had different precipitation data sets and we want to estimate recharge, we're going to have uncertainty coming off from those input data sets. So at the end of the day, I think there are different sources of uncertainty. The primary one you are talking about is coming off model structure and parameters, but we also have the one associated to input data sets. So I just wanted to get to know your thoughts about those different sources of uncertainty and how to deal with those as well. For example, I was thinking if we have only one model structure and one model parameter set and multiple input data sets, we also are propagating uncertainty through the model structure and parameters. So I just wanted to get to know your thoughts about that, and what do you think about those different sources of uncertainty?
What you say is true, of course, Rodrigo. As I said before, when it comes to uncertainty, seek and you will find. Now, like in a Bayesian world, so if you're uncertain, for example, about past recharge and past pumping, for example, ideally, they can also be parameters. You can then provide past recharge in a probabilistic sense. And because as inferring, if you get that wrong, your parameters are going to be wrong, and then your predictions are going to be wrong because they're calibrated on the basis of an assumption. The more assumptions that you can turn into probability distributions, the less bias you have, the more you turn bias into quantifiable uncertainty. Now, that's the theory.
Right.
If you're saying that's going to be difficult to implement sometimes, and this may cause you to have different models based on different assumptions, that may be the case. Now, for me, I like to avoid that if possible. If I can perhaps take structure, abstract things a little and turn structure into a parameter, I try to do that. But that means there's possible bias incurred by turning structure into a parameter, and it mightn't work.
Right.
So, Rodrigo, it's just another one of those compromises. You have to recognize it just as you've done, and then do what works for you according to the prediction you got to make. But what you say is totally true. I can only agree.
I would like to comment on the last two questions, Rodrigo, and the previous one about climate change. I just got an idea here. I think it would be a very good exercise. We have been talking about climate change at least for the last 30 years, seriously. I remember there was this movie, I think was called The Blue something with Al Gore, everything. That was mid-90s. And since then, many things has happened. We know that the climate is changing all around the world. So we had news from everywhere that things doesn't fit well with the historical series. So it would be a very good exercise to see what the model predicted, the model that were around 20 years ago were predicting for today. And just to have a sense of the uncertainty that they were predicting, how it compares with the real situation now. Are we within the uncertainty range that they predicted, or are we outside that range? It would be a nice exercise, I think.
Yeah, definitely that would be a good exercise. I think there are a few papers that have done that already. But yeah, definitely.
That's interesting. Yeah, there must be. Yeah.
Thank you so much for your answers.
Paulo, ¿te parece hacer
Thank you. Sí, yo creo que...
Sí, yo pienso que también ya por la hora se ha desconectado bastante gente para no abusar de los expositores ni también de la audiencia. Vamos a dar por finalizado este webinario, dando las gracias a Paulo, John, ¿verdad? Ha sido una excelente presentación, un muy buen tema, ¿verdad? Hemos tenido participantes que habitualmente no tenemos, lo cual como Alhsud nos sentimos contentos de poder extender nuestros vínculos y nuestros, ¿verdad? Seguidores. Así que, thank you very much, John, ¿verdad?
My pleasure.
Pablo, y a todos los asistentes.
Muchas
Les
gracias.
recuerdo que esta presentación, así como las consultas y todo, quedan grabadas en la página del Alhsud. Normalmente nos demoramos unos días en subirla, pero se pueden consultar ahí después las ponencias y todas nuestras actividades. Que estén muy bien.
Thank you, Carlos, for the translations.
No worries. Happy to do that, and it was fantastic for me being a lawyer to try to understand everything you said. So we are so happy in Alhsud, John, to having people like you and Paulo expanding our frontiers with professionals of your caliber abroad. So thank you very much for taking the time to share your knowledge and wisdom with us, and looking forward to have you in the future.
Yes, the last words in Spanish. Gracias a todos, muchas gracias.